Just a moment. Where is it? Okay. We have to synthesize this compound. As you know, we can apply a retrosynthetic method. And so first of all, you see this is an ester. It's very easy to hydrolyze. To hydrolyze this compound. So, for example, we can hydrolyze the ester. And so if we apply a retrosynthetic method, you see we have this alcohol. Okay. It's very easy to form an ester in this position. And then another simplification by applying the retrosynthesis is to break this type of bond, you see, because we are able to synthesize this type of bond, we'll see the reaction. So we start from these two compounds. Here we have a double bond. We can make better, just a little better. No. So, can make this one. It's a ketone. And then here we can have this type of compound. This means that we can perform a Grignard reaction starting from the 4-piperidone. You see 1, 2, 3, 4 piperidone with this Grignard reagent. Why it is necessary to use this type of reaction? Because you know very well the polarization of the carbonyl group. If you have a positive carbon atom and the oxygen is negative because it is more electrophilic. And then if you want to have a reaction with this carbon atom, it is necessary to have a negative carbon atom. And so we need the Grignard reagent. Grignard reagent, you know, the polarization. The magnesium has a positive charge and the carbon has a negative charge because carbon has more electronegative, yes. So in this case, you see the arrow, you have this type of attack. And then we have a tertiary alcohol. Tertiary alcohol. The problem is at this point. Why? We have to synthesize an ester. So this alcohol should react with an activated carboxylic acid, in particular propionic acid, to give the ester. So we can describe the reaction. We can take this one, this point. We can take the arrow, and then No. Okay. And make again. To give methyl piperidine phenylpropionose, MPPP. During this reaction, as you know, there is the release of hydrochlorhydric acid. This is the problem, because tertiary alcohol in acidic condition can lose a water molecule to give a double bond. I show you now what happens. So we can have this type of molecule. Okay, it's not so good. Okay. And yes?
I don't know if this is, you are sharing this, I don't know.
Yeah.
If you are sharing on Teams, this.
Okay, okay. Oh, sorry. Sorry. Okay. Now? Okay. Sorry. So, the problem was at this point. Because in the mix, the final product was formed by a mixture of MPPP with this other compound with this double bond called MPTP. MPTP. M means methyl, P means phenyl, TP is tetrahydropiperidine, just to indicate the double bond.
We have two products.
Yes.
MPP.
A mixture of these two compounds. A mixture of MPPP, this, the desired compound, but with a lot, about 50% of MPTP as contaminants, but in a very high amount. And the problem is related to MPTP, because this MPTP can be metabolized by MAO-A, monoamine oxidase type A, and can be transformed in an aromatic ring. You see now. So we have this situation with a positive charge on nitrogen. There is a positive charge here. Okay. And this compound is called MPPP+. This means methyl, once again, P-phenyl, once again, and PP is piperidinium. Piperidinium means a salt of piperidine. This compound, this MPPP+, is a substrate or a specific reuptake system of dopamine inside the dopamine neurons, And so MPPP plus, it is reuptake, it is a substrate for the reuptake of this transport system. And so it is concentrated only in the dopamine neurons. So MPP plus is a specific substrate for this type of reuptake system, but also is a strong toxin for the mitochondria present inside the dopamine neurons. This means that with this toxin, we are able to hit only dopamine neurons and not neurons of other systems. It's very, very selective and specific. This compound is able to kill only the dopamine neurons because it is able to block the activity of the mitochondria inside this type of neurons. This means that the first students that used this compound, that immediately, after a few hours, by fulminant Parkinson. In that time, this student wrote a lab book. A lab book, you know, when you are in a lab, you write on your book the experimental condition and so on. And this book was founded some years later by other 5 students of chemistry of the same college. But at that time, they didn't know that the first student died after the use of this compound, because in that time, no investigation, nothing, and so perhaps they thought that the student had a heart failure or other problem such as this. And these 5 students synthesized again this compound, they used again this compound, and they died altogether. So other 5 students died. The sheriff of that region started an investigation, and they found some samples of this compound in the lab. They found the description and the synthesis of this compound, and so they started a wide investigation in the field of drugs, American drugs, free drugs. And they found that other people at that time used this type of compound, and other people had the same problem. Is it clear, this synthesis? It's very easy. Grignard reaction and then esterification, 2 steps. Very, very easy. And so you can imagine a chemist student try to make this reaction in lab. 2 steps, very easy. You can see the story. A moment. Where is here? Okay. You can see in this article the story of MPTP. William Langston was a scientist in California, you see here. He was a medical doctor. He worked in a hospital, a geriatric hospital. And he received in that time a lot of communication about strange effects on a lot of people which used a synthetic heroin. You see here in yellow the important point of this article. This is it's not an experimental article, it's called a review. You see here a review. A review is a collecting article in which a scientist describes all his experience and put together all data. It's like a wide description of the whole story related to MPTP. And so they found at the beginning several patients with a totally unresponsive, with this type of fulminant Parkinson. But in that time, they didn't know any effect of MPTP on dopamine neurons. Some years later, they were able to obtain samples of the synthetic heroin, and they found MPTP as byproduct, contaminants of MPPP, you see. And so they started an investigation about this compound. They tried to elucidate, to understand the mechanism and the toxicity of this compound. In particular, they induced virtually of the motoric and some non-motor features of Parkinson's disease. You see, they found something very similar to Parkinson's disease in these patients. In particular, they found a nigrostriatal degeneration. Okay. The discovery of that this compound is toxic toward only dopamine neurons represent really a milestone in the investigation of this disease. And in particular, it was possible they had in that time a human model of the animal model of human disease. So really, it was an important discovery to have a selective toxin only towards the dopamine neurons. They discovered also that MPPP plus was an excellent substrate for dopamine uptake site, you see. Something about the mechanism. And in particular, they found that this compound is able to trigger the formation of a high number of ROS, of radical species inside the dopamine neurons. This fact, represents the starting point of the modern investigation on the neurodegeneration diseases, such as Parkinson, but also Alzheimer's disease. Alzheimer's disease is another important disease which involves the neurons, the neurodegeneration of all neurons. So if you want, I can send you this article. It's very, very interesting. The last point, modeling Parkinson's disease, is example of the translational impact, how we can use this compound in clinical trials. So they can they can have a model of Parkinson's disease in primates, monkeys. And then they started also to identify a therapy against Parkinson's disease. And in particular, they thought that by blocking MAO-A, it was possible to have a therapy against Parkinson's disease. This because MAO-A is responsible of the oxidation, it's a reduction, yes, a reduction of MPTP to MPP plus. And so they thought in that time that if we block this type of enzyme, it is possible to have a therapy against Parkinson. These represent the first hypothesis, the first therapy for Parkinson. And it was possible thanks to the discovery of the activity of this type of toxin. Okay. At the end of the article. Which is the etiology of this disease? This is a big question. There are two schools of thinking. Environmental hypothesis by pesticides, because several pesticides are chemical structure very similar to MPTP. Or genetic. So the discovery of this type of toxin increased the score of the environmental hypothesis. And so perhaps the appearance of this disease can be related to exposure of humans to pesticides. This can represent one of the first hypotheses to explain why Parkinson's disease appears in some guys and not in other guys. Perhaps it is a mixture of, I think, of genetic and environmental reason, I think. This is my personal opinion. Okay. I read this article just yesterday night, and it's very, very nice. Okay. Just to explain you how it is possible to try new compounds by starting from clinical observations and from those students who died in the 70s. Okay. Once again, going back to our slides. You see here, just a scheme, MPPP, heat MPTP, in acidic condition, you have dehydration, so loss of a water molecule, formation of the first double bond. MAO-B, you see what happens. MAO-B, autooxidation, MPP plus, uptake by neurons, metabolic chains, nigrostriatal cell death. Selective induced Parkinson's disease. You see here the toxicity against the mitochondria. You see mitochondrial dysfunction, and so a selective death of dopamine neurons. Here you can see a scheme about the motor nerves. Motor nerves, the activity of the motor nerve is influenced by two important neurotransmitters. Acetylcholine is in an activator, and dopamine, which is an inhibitor neurotransmitter. related to GABA, to a prefiber of gamma-aminobutyric acid. So the problem is, when there is the Parkinson disease, we have a decrease of dopamine. This means that we have an increase in activity of acetylcholine, which is an activator of the motor nerves. So if you want to treat this type of disease, we have to increase the concentration of dopamine inside the motor neurons, or by agonists, of course, or by indirect agonists by increasing dopamine. Or we can decrease the activity of acetylcholine by using selective antagonists. These are the two strategies to treat Parkinson's disease. We can increase the dopamine concentration in motor neurons by specific selective agonists or in an undirected way, or we can block the increased activity of acetylcholine by using specific antagonists. For the moment, these are the only two strategies, because you can imagine, if it would be possible, we have to restore the dopamine neurons inside the substantia nigra, but at the moment it is not possible. The same approach is for Alzheimer's disease. You know that Alzheimer's disease is the problem is represented by the death of a lot of neurons inside the brain. So the treatment should be to try to restore the number of neurons inside the brain, but it's not possible. So at the moment, we try to increase the activity of the few neurons remain in the brain, or in this case, we can increase the activity of dopamine by using specific agonists. We have two types of agonists: undirected agonists and directed agonists. If you remember, I have already shown you these slides, just a moment. Here. If you remember, the starting point of the biosynthesis of dopamine is tyrosine, which is hydroxylated to L-DOPA, and then L-DOPA, by the carboxylation, we have dopamine. Dopamine is not able to cross the blood-brain barrier, so we can assume L-DOPA. L-DOPA is able to cross the blood-brain barrier thanks to the presence of specific transport system of the amino acids, dedicated to amino acids, and in this way, L-DOPA can be transformed in dopamine inside the CNS. But the problem, this type of approach has a problem. See here. If we assume a big amount of L-DOPA, L-DOPA can be transformed in dopamine also in the periphery system, not only in CNS. And the transformation of the L-DOPA in dopamine in the periphery system is responsible of severe side effects. The first one is the strong vomiting. Dopamine is an agonist on the stomach, and we have a strong vomiting by patient. Second, are related to effect of dopamine on adrenergic receptors. For example, alpha-adrenergic receptor causes vasoconstriction, you see, or beta-adrenergic directed on the heart can stimulate the heart frequency. So the problem is, we can assume L-DOPA, yes. L-DOPA is inside our body, yes. Part of this L-DOPA can be transported inside the CNS, yes. But the most of dopamine remains in the periphery system and can be transformed also in the periphery system in dopamine. And then we can have a lot of severe side effects. The stomach, the vasoconstriction, heart frequency. How we can avoid these side effects? Is it possible? Yes. Together with L-DOPA, we can assume an inhibitor of DOPA decarboxylase, of the enzymes responsible of the transformation of L-DOPA to dopamine. An inhibitor of these enzymes called the carbidopa, but this inhibitor should remain only in the periphery. Unfortunately, carbidopa is too polar, and so it is not able, carbidopa, to cross the blood-brain barrier. So the strategy is L-DOPA, yes, but together we can associate also an inhibitor of peripheral DOPA decarboxylase, and this inhibitor can be carbidopa, the most famous, or benserazide, the second one. But carbidopa is the most known and the most famous. Can we see the chemical structure of carbidopa? The problem is we have to inhibit an enzyme responsible of the decarboxylation of L-DOPA to dopamine. Yes. We have to block this enzyme. So it is necessary to design something very similar to the substrate. If you see the chemical structure of carbidopa, once again, you see the same aromatic ring, 2 OH groups, phenolic OH, okay. And the same chain, 2 carbon atoms, unacidic groups, a basic group. But in this case, the basic group is more basic than the amino group present on L-DOPA. We have 2 nitrogen atoms in this case. It is called hydrazino group. Hydrazine is NH2, NH2. 2 nitrogen groups. So carbidopa is very, very basic. Very, very polar, protonated at physiological pH, so unable to cross the blood-brain barrier. So you can understand the strategy. And you see Cinemet is the commercial name of this preparation of the association of L-DOPA with the carbidopa. And then it is easy to remember the chemical structure. Carbidopa is very similar to the substrate, to the L-DOPA. We have an hydrazino group instead of an amino group, and a methyl on carbon 2. The other strategy is to block the metabolism of dopamine. If you know, we have already described this, the different strategies, how we can increase the concentration of a neurotransmitter inside the synaptic cleft. In this case, we can block the monoamino oxidases. In particular, you see selegiline is able to block the monoamino oxidases, or catecholomethyltransferase. It is the other class of metabolic enzymes of dopamine, entacapone in this case. A consideration just on selegiline. Selegiline is an inhibitor of monoamino oxidases. This means that selegiline is able to increase the concentration of dopamine inside the synaptic cleft. Okay. But selegiline is able to block also the metabolism of other neurotransmitters, such as noradrenaline, such as serotonin, other neurotransmitters involved in other important functions. And in particular, we'll find this compound between the antidepressants, because selegiline is able to increase the concentration of other important neurotransmitters involved in the depression. But at the moment, we are interested only on the activity of selegiline on dopamine synapses. There is another compound called amantadine. We have already seen this compound as antiviral drug. This compound is able to block the uncoating of the viruses inside the cell. In that time, medical doctors observed that when this compound was used in the old people with Parkinson, this compound was able to ameliorate the symptoms of Parkinson in these patients, in these old patients. And it was observed that this compound is able to increase the release of dopamine inside the synaptic cleft. The mechanism is unknown, but they saw a real benefic effect of this compound for the treatment of Parkinson. So you have also this compound as indirect agonist. It is able to increase indirectly the quantity, to increase the release of dopamine inside the synaptic cleft. Have you any questions on this point? Clear or clear? At home also? Yes? Okay. And now...
Yes, Prof. It's not clear.
Thank you. Direct agonists. Just to begin this point, it is necessary to make some observation about dopamine. Once again, dopamine is not able to cross the blood-brain barrier. Sorry, it's BBA, but it's BBB. Another point is that dopamine is unstable, can be metabolized by MAO, monoamine oxidases, and catechol-methyltransferase. These two classes of metabolic enzymes. The other point is that dopamine is not selective. We think that selectivity towards the different receptor subtypes is due by different conformation that dopamine can assume during the interaction with the different receptor subtypes. So it is necessary to have a frozen analog, a frozen compound, not able to give a lot of conformation such as dopamine. And so the scientists try at the beginning to find the active conformation of dopamine on D1 receptors, postsynaptic receptors, and then to have a compound able to cross the blood-brain barrier. And finally, to be not metabolized by COMT or MAO, monoamine oxidases. What about dopamine? Structure-activity relationships. We start from the amino function. Amino function is too polar, too basic, and it was found that it is possible to add two groups on the amino function, in particular two normal propyl groups, 3 carbon atoms. This means in this way we can increase the lipophilicity of dopamine. And this substituted molecule with the two normal propyl groups is able to cross the blood-brain barrier. Although the basicity of the amino group, but in this case there is an increase in lipophilicity. And these two propyl groups probably find a pocket on the active site of the receptor. There is a pocket where these two groups can be accommodated. The length of the chain is critical. Only 2 carbon atoms. No any other groups on this chain if we want to have a direct agonist. What about the catechol ring? Catechol 2 phenolic OH groups. If you remember, the catechol or methyltransferase, this class of enzymes, is able to transfer a methyl group on OH in meta position, and this means that the most important OH is the OH in meta position, because if the enzymes attack this OH, probably is due because this OH is the most important. The OH in 4 in para position is not important. So cannot be present. If the OH in 4 group is not present, the catechol ring cannot be attacked by catechol or methyltransferase, because this type of enzymes are able to attack only the catechol system, not a simple phenol group. Phenol is 1 OH, catechol is 2 OH. So during the direct agonist, we'll see molecule with only a group in a meta position, able to give hydrogen bond. The function of the OH in 3, the most important OH of the ring, is to give an additional hydrogen bond with the receptor. The OH in 4, not. All these indications were used to design the first direct agonist, called ropinirole. We can see the chemical structure of ropinirole. The nitrogen atom you see with the 2 normal propyl groups. We have described that it's possible to insert these 2 groups on the amino group of the dopamine. Okay. Ethyl chain, like in dopamine, aromatic ring, okay. And then in meta position, in 3 position, you have an amide. Lactam is a cyclic amide. Why an amide? Because you see there is a proton, an hydrogen, able to give an hydrogen bond with the receptor. The same function of the OH in 3 on dopamine. So the indole nucleus, all these nucleus you see, an aromatic ring with this nitrogen ring, is called in an indolic system. The indolic system is able to replace the catecholic ring of dopamine. But in this way, ropinirole is not attacked by catechol-methyltransferase, is resistant towards this type of enzyme, cannot be attacked by monoamine oxidase because there are these 2 bulky groups, normal propyl groups on nitrogen atom. So ropinirole represents the first direct agonist of dopamine on dopamine receptors. Have you any questions? What about the second class? You see here on the top the simplified structure of dopamine with the additional groups that we have already described. In particular, you can see the nitrogen atom with 2 normal propyl groups, and then you see a phenolic ring only with OH in 3. the most important OH able to give the hydrogen bond, an hydrogen bond with the receptor. What about the scientists? As I told you before, the scientists tried to find a frozen analog of dopamine. So they tried to block the conformational freedom of dopamine by introducing some cycle inside the chemical structure of dopamine. Here you can see the strategy. They took the normal propyl chain of one of the substituents of nitrogen and they closed the ring. You see, they closed the ring to give 3-phenylpiperidine. 1, 2, 3-phenylpiperidine. In that time, they found some interesting compounds in this class, but no drugs. And so in this class, we cannot find any drugs as directed agonists. But it is interesting to describe you the strategy. The introduction of a cycle by incorporating the normal propyl chain of one substituent. Nevertheless, that time they didn't find any drugs in this class. Another strategy, they closed the ethyl chain in a ring. No more the normal propyl chain, but the ethyl chain. You see here, we have 2 amino tetralines. You see, once again, this is the ethyl chain with the amino group, and you see the ethyl chain was incorporated inside a cyclohexane. We can have 2 different amino tetralines, which differ from the position of the 2OH on the catecholy ring of dopamine. You can see on your left the chemical structure corresponding to trans-beta alpha rotamer, and on your right, trans-beta beta rotamer. Once again, I remember you the active conformation of dopamine that we have found inside the apomorphine is related to trans-beta alpha rotamers. Starting from this point, the scientists designed other indirect agonists. You see here an application of the observation already found in the first class On the nitrogen atom, the insertion of 2 normal propyls. Okay. The ethyl chain was incorporated in a cyclohexane cycle just to block the conformational freedom. And then the 2 OH group corresponding to the trans beta alpha rotamer. In this class, we have 2 drugs. The first one is rotigotine, which is the chemical structure of this compound. If you see, once again, you have the same system of aminotetraline in which the OH correspond of the OH in 3 of the trans beta alpha rotamer. Once again, on the nitrogen atom you can see a normal propyl chain, and in addition a thiophene, an aromatic ring on the nitrogen atom. Why? Because we have to increase the lipophilicity of the compounds in order to increase its crossing of the blood-brain barrier, the entrance of the influx of this compound inside the CNS. So, rotigotine derived directly from the observation of the aminotetralines with the addition of an aromatic ring on the nitrogen atom. The second one, another important compound of this class, is called pramipexole. Can we see the chemical structure of pramipexole? On nitrogen atom, once again, normal propyl chain. Nothing new. The ethyl chain is incorporated in a cyclohexane. Nothing new. The catechol ring of dopamine is replaced by aminothiazole. Aminothiazole, we have already seen this type of heterocycle in cephalosporin. It is able to give hydrogen bond. And in this case, you see this NH2, this basic group, can give hydrogen bond with the dopamine receptor, working in the same way of OH, of phenolic OH in 3 position. So also pramipexole represents a direct drug of aminotetraline, but the catechol ring is replaced by aminothiazole ring. So these are the 2 most important compounds of this class. Rotigotine, on this agonist you can find again the active conformer of dopamine, and the pramipexole, in which the catechol ring is replaced by aminothiazole ring. Have you any questions? No? Okay.
No, Prof.
Okay. We can stop for 15 minutes, okay? And then we start again at 11:30, okay? Okay. So Yeah,
You say the classical chain is replaced by amino, is it thiazole or thiazole?
what's, sorry.
The amino group,
Yes, here.
yes, is replaced by.
No, okay. This NH2 has the same function of the OH in 3 position. If you remember in the dopamine, the most important OH is the OH in 3, and this NH2 has the same function to give an hydrogen bond with the receptor. Clear? Okay. Any other questions? No? Okay, so then we start again later with the apomorphins. Okay? Okay. che sei qua. Okay. So we start again. We have seen the two different classes. The first one, phenylethylamines, phenylethylamines. The second one, the three phenylpiperidine. The third one, 2-amino tetralines. And then the last one, aporphins. This skeleton, this backbone, is common to different natural products, but it is also possible to have this type of system by acidic treatment of morphine. We'll see in the next lesson the chemical structure of morphine is formed by 5 rings, by 5 condensed rings. And you see the catechol ring, the ethyl with the second cyclohexane. Also, the nitrogen atom is inside a cycle ring, and there is also an additional aromatic ring. So we can go just on ChemDraw. Just a moment. Okay. Where is ChemDraw? ChemOffice, ChemDraw. Okay. And then I share, just a moment. Share ChemDraw with you. Okay. The question is, how we can remember the structure of morphine? Normally I start from the active conformer of dopamine. If you remember, this is the active conformer of dopamine, trans beta alpha rotamer. Okay. And then we can close the first ring here. See? We can add the second ring here. And then we can insert the third, an aromatic ring. So in this way, I think it's easier, if you want, to remember the chemical structure of this complex molecule, this complex class. And once again, I want to show you the active, oh, sorry, why double? Just a single. Okay. Okay. You can see here the active conformer of dopamine inside this very, very rigid, very tough backbone. The activity of this compound allowed us to understand the active conformation of dopamine with the receptor, at the active site of the receptor. So really, in this way, it's possible. It's very easy to design, to draw. Sorry, to draw the chemical structure of this class of molecule. Back to slides, just a moment. Okay. Okay. We can start from apomorphine here, and then we can simplify the chemical structure of apomorphine to give 2 amino tetralines. Then once again, we go to the first class related to dopamine, phenylethylamine. Apomorphine is one of the most potent agonists, dopaminergic agonists. It is used to treat Parkinson's disease, and it has a strong effect on stomach to cause vomiting. It is a vomiting agent, very strong. It is used also in case of ingestions of poisons, toxic compounds, because it has really a strong effect on the stomach. All these agonists, direct agonists, have a potent effect on stomach, on the dopaminergic receptors located in the periphery, and so they have this type of effect. Once again, you can see the active conformation of dopamine inside the apomorphine. There is also another class of compounds used for the treatment of Parkinson. And this compound, this class is formed by natural compounds. I'd like to describe you ergotism. Ergotism is a disease which derives from the ingestion of particular compounds related to a fungus called Claviceps purpurea. Perhaps you have already heard this type of parasite. During the Middle Age, there were a lot of diseases. One was the St. Anthony's fire. And some of these diseases, the population believed that these diseases were related to sacred fire or evil. And because these type of diseases are very common, and they involved a huge number of people. In particular, ergotism was often fatal, devastating effects. The attack of this fungus, Claviceps purpurea, which contains ergotamine and other compounds, caused intense peripheral vasoconstriction. So a strong effect on the adrenergic, alpha-adrenergic receptors. In severe case, can lead to gangrene of the limbs. So no more blood to the muscle due to this strong vasoconstriction. The intoxication, the acute intoxication is manifested by diarrhea, vomiting, colic, headache, dizziness, tremors, convulsion. You see a picture of a disease from Hevil. Chronic intoxication produces difficulty in walking, muscle pain. It seems a God's damnation. In this class of compounds, we'll find a compound called LSD, lysergic acid diethylamide. It is a famous drug used not in therapy, but for other applications, we can say. Because these compounds are able to give hallucinations to the patients, to the people. The intoxication from these products can be found also recently. You see, during 19th century. And in 1953, the Swiss chemist Albert Hofmann, a very famous chemist, discovered the importance of these alkaloids. In particular, you see lysergic acid. Other case of intoxication in Milan, in Turin, in Europe, 51. And the reason of this intoxication, the cause of intoxication is this parasite called the Claviceps purpurea. It is a parasite of gramineous plants. Claviceps purpurea form a sclerotium similar to small horns. Yeah, so the name, it is able to infect the plants, and the common name is ergot from the French. It is able to infest grain, and so this fungus is present inside the grain, and it is an important contaminant. It's called mycotoxins. But which are the chemical structure of these alkaloids? You can see in this picture this very complicated the chemical structure of this compound. 4 rings A, B, C, D fused together. But why this type of alkaloids are able to interact with the dopamine receptor? Are there some chemical features common to these alkaloids and also to dopamine? Can we find some features? Can we find the active conformer of dopamine inside this chemical structure? Okay, first of all, we have a basic function. This nitrogen atom in 6th position, you see. And then you see an ethyl chain, 2 carbon atoms. Once again, an aromatic ring. Once again, another basic group in 3 position of the aromatic ring in meta position, able to give hydrogen bond with the receptor. So once again, inside the chemical structure of these derivatives of ergot, you can identify the active conformer of dopamine. This is the reason of the effect of this compound on the dopaminergic receptors. Because inside their chemical structure is possible to identify the active conformer of dopamine. But the question is, how many of these active conformers are present inside the chemical structure of the ergot derivatives? Here you can see the first one, but on your left in black, you can see also a second possibility. Nitrogen atom, ethyl chain, aromatic ring with a group able to give hydrogen bond. So the scientists identified two different parts of the molecules which have the same chemical features of the active conformer of dopamine. And they try to verify which of the 2 parts are responsible of the dopaminergic activity. So the scientists synthesized the 2 different parts of the molecule to verify which of the 2 parts was responsible of the dopaminergic activity. Here you can see in black the first one. You see here nitrogen, ethyl chain, aromatic ring with OH. On your right, you can see the second in red, nitrogen, ethyl chain 1 and 2, and then an aromatic ring. These 2 different compounds were synthesized, and the scientists found that both were active as dopaminergic agonists. So we cannot say if the dopaminergic activity is related to only one or to both parts of the molecule. The final result is that this compound, these alkaloids, have a very potent activity on dopaminergic receptor. They are endowed with a very high dopaminergic activity. So here you can see a long series of this compound. These compounds are not requested during the exam. I understand the complexity of these structures, I know. But I want to explain you how it's possible to identify inside this chemical structure a common structure with dopamine, the active conformer of dopamine. Here you can see lisurite, bromocriptine, pergolide, pergolide. These compounds are used for the treatment of Parkinson's disease. Very, very potent. And you see the insertion of a bromine on bromocryptine just to increase the lipophilicity. It's a semi-synthetic compound. LSD, the diethylamide of the lysergic acid, you see here the acidic function. If you want to increase the lipophilicity of this class of compound, we have to transform, to mask this acidic function in an amide. So we go in on the ChemDraw, just a moment. Okay. Then I share the window. Okay. We have seen that there is an acidic function here. We want to increase the lipophilicity. We can transform this acidic function in an amide, like this one, just to understand. Okay, so can put nitrogen here. So in this way, you see, we have transformed the acidic function in an amide, which is less polar. It is not ionized. And so the LSD, the diethylamide of lysergic acid, can reach very easily the CNS. This is the transformation that the chemists make on these molecules to increase the lipophilicity, to increase the activity of the natural compound. Okay, back to the slide again. Here. Okay. You can find here some structure activity relationships of this class, but as I told you before, these compounds are not requested during the exam. Okay, other compounds, cabergoline, dihydroergocryptine, you see, very, very complex structure. Okay. So, at the end of the lesson, we had a simple synthesis of carbidopa. What is carbidopa? Carbidopa is very similar to L-dopa. Just a moment. We can go to ChemDraw here. And then we share the screen once again here. So here. We have the the 2OH here and here. And then we have here. Perhaps was too much. It doesn't look, yes, not on this one. Yes. This way. Okay. And then we have a methyl group here. Yes. If you see the chemical structure, it's like an amino acid. The amino group is replaced by the hydrazino group, but there is still the acidic group. So the synthesis of this compound is very similar to the synthesis of amino acids. We can see how we can synthesize an amino acid. We can start from a ketone, for example, or from an aldehyde, perhaps it's better. Here. You can see an aldehyde with the pair in this position, very general. It's possible to introduce in the same time an amino group and a carboxylic group on this structure. So we can get the result, the final compound can be a compound like this. Here NH2, here COOH. So it is possible in one step to introduce a carboxylic, an acidic group, a carboxylic group and an amino group to get an amino acid. This reaction is called Strecker reaction. Strecker with E. The reagents are ammonia and cyanhydric acid. So we can put together ammonia and cyanhydric acid together with the aldehyde, and then in one pot, in one step, we can have an amino acid. Which is the reaction? At the beginning, the first step, if you remember, the ammonia group has the lone pair here, and so the lone pair is able to attack the aldehyde group in order to give the Schiff base. So an arrow here, and then we have this type of compound. we have a loss of one water molecule. We have already seen this type of reaction. And then we have the formation of imine. Which is the polarity of this compound? We have a positive carbon atom and a negative nitrogen atom. So there is a hydrogen here. Partial, okay, partial positive carbon atom and partial negative the nitrogen atom, because the nitrogen is more electronegative than the carbon, and so we have another hydrogen here. Okay, this is the polarity of the Schiff base. So at this point, it is possible the attack of the Cn minus ions to the positive carbon. You see? So the product is this one. We have our air here, we have NH2 here, and then we have C, triple bond, N. A nitrile group. Nitrile group is a masked acidic group because we can hydrolyze nitrile in acidic condition, perhaps. And then we can get the carboxylic group. This reaction is called the Strecker reaction, and so we can use the ammonia with the cyanhydric acid, and the final compound is an amino acid. The same reaction can be applied for carbidopa, but instead of ammonia, we can use hydrazine. Hydrazine is NH2, NH2. It's very basic, can attack the aldehyde, can give a similar Schiff base, and then the Schiff base can be attacked by the cyano ions, cyanhydric ions. So we'll see this type of reaction to give carbidopa, and then go back again to slides here. The starting point is represented by a ketone. because we need, if you remember, on the carbidopa, we need a methyl group on the carbon atom in 2. You see the first reaction. Potassium cyanide and hydrazine. Potassium cyanide is able to give the cyanide ions, and hydrazine is able to give an attack to form the Schiff base with the ketone. Yes.
Why there is the methoxy group?
Yes, it's just a moment. It's just to protect the OH in this condition. This is the difference, okay? Just at the beginning, I want to explain you the reaction to give the amino acid, and then we see the particular reaction to give a carbidopa. Okay, so the first point is to introduce, you see the cyano group and the hydrazino group on this carbon atom, the carbon atom and the carbonyl, the ketone. You see there is a methyl group on the OH in 3, in meta. This methyl group is to protect the group from the oxidation, from the condition of the reaction. It is an ether. So the next point is to hydrolyze the nitrile, the cyano group, to amide. Is a middle hydrolysis. It's the first hydrolysis from the cyanide to amide. Then at this point we have to hydrolyze again the amide to carboxylic acid, and in addition we have to deprotect, we have to hydrolyze this ether group, this methyl, to give the free phenolic group. So we need a very strong acid, hydrobromidric acid, and this 48%. This acid is able to hydrolyze the amide to carboxylic acid and to hydrolyze to release the phenolic OH in 3 position. So this is the reaction to give carbidopa. Once again, you can see here on your left the mechanism of Strecker reaction. This type of reaction able to give an amino acid function, amino acidic function. You see the aldehyde reacts with the ammonia to give the Schiff base, and then the attack of a cyano group to give this amino nitrile. And here you can see the hydrolysis of the amino nitrite to give an amino acid. The same reaction is applied for carbidopa. First step, potassium cyanide, very toxic, I remember you. In acidic condition we can have cyanidric acid, very toxic. The gas chamber of the German during the Second World War. Hydrazine, able to give the shift base, attack of the Chano group, the first hydrolysis, and then the last hydrolysis to release the OH and the carboxylic group. Have you any question about this reaction? Perhaps you have, yes.
Could you repeat the name of the reaction?
Strecker, you see, where is, just a moment. It's not, okay, you see here,
Okay.
if you click, perhaps you can find also on Wikipedia, you can find the mechanism.
Oh, okay. And is it the name of the whole?
Strecker is the first step when you put ammonia with the potassium cyanide together.
Okay.
This is the reaction. Yes, you can find a lot of reaction on the web, and in particular there are some interesting sites with the mechanism of the reaction. So perhaps if you want to know some details about the reaction, you can see on the web. A lot of universities have published some movies about the reaction, the mechanism, and so on, really. It's very easy to find the description of this type of reaction on the web. You see also on the Wikipedia a lot. You can see all the mechanism if you want to see. Okay. Other questions? No more? Tom, have you any questions?
No, it's clear. Thank you.
Yeah. Okay, so with this synthesis, we can close this chapter about the dopaminergic agonists. And then I want to introduce very briefly the next chapter about the dopamine antagonists, just to have a general description of this chapter. Just a moment. I close this one. I close this one. And then we can go. Dopamine antagonist. Let's see. We have already described the importance of agonists, of dopamine agonists to treat Parkinson's disease. But in 52, some medical doctors observed some interesting side effects of a class of particular compound able to antagonize the activity of histamine. In particular, they observed the behavior of the patients after administration of potent antihistaminic drugs. This type of compounds were used against all the effects due by an allergic reaction from natural compounds, chemical compounds, what you want. This type antihistaminic drugs are used to treat locally on the skin or in our body the allergic reaction about against different compounds. But an important side effect was due by a strong sedation of the patient. The patient which uses this type of compounds has no forces. He tries to sleep, to stay on chair without forces, without any other reaction. And so the scientists tried in that time to amplify this side effect in order to have a strong sedation of the patient. This type of compounds are used against violent patients. You see every day on the journal, on the newspaper, husband killed wife, daughters, sons, and so on. Just yesterday, the last case. And so it is necessary to have this type of compound to control the violent attack by this patient. So in 52, the scientists investigated very deeply the structural activity relationships of antihistaminic in order to amplify this particular side effect. The prototype of this class, just a moment, oops, is promazine. Promazine was one of the first antihistaminic agents, very potent. You see the chemical structure of promazine here. A very planar region, 3 rings, 666 system, a basic chain. We are talking about the dopaminergic system. You know dopamine? Dopamine is formed by a basic nitrogen atom and an aromatic ring. So, if we want to block the active site of this type of receptors, we need a molecule able to have stronger interaction with the receptor. And so it is necessary a basic nitrogen atom, of course, but also a wide planar aromatic system. You see 666 system. It's very common in this type of compounds. And the scientists in that time investigated the structural activity relationship very deeply, and they found that it was possible if we change the aliphatic chain from normal propyl to isopropyl. So we change the position of only one methyl group. We have a potent amplification of the sedation of this side effect. So you can see a small chemical change is able to give a potent effect. This is the point. So here you can see a lot of other compounds. So the next time I want you to describe a lot about schizophrenia, how this type of compounds can be used for the treatment of this disease, and in particular, which type of compounds are used in the treatment of schizophrenia, and then we'll see the different classes of these compounds. So this is just a brief introduction on this chapter, and then we'll see better this class of compounds. So, have you any question at the moment? Classroom? No, nothing. At home? No, okay. So next month, we see next Monday in the afternoon, and then we start with this chapter. And then, as I told you before, I want to finish the course about the 24th, 25th of May. Yes?
If I understood clearly, what's the relationship of these antihistamines to
Yes.
the dopamine?
Antihistamines were as used also today for the treatment of allergic reaction, But if you assume this compound orally, for example, you have the anti-allergic effect, of course, but also a strong sedation. In particular, of the old antihistaminic. Now the second and third generation no more, but at the beginning, the phenothiazine group have a very strong sedation effect. And then the scientists wanted to amplify these side effects to transform this side effect in the main effect, and to have a class of compounds with a strong sedation effect, and no more an anti-allergic, but a sedative agent, a strong sedative agent against the violent attack from patients. To control this type of patients, it's not easy. But really, the patients can lose all forces, no more forces in the muscle. So they stay blocked on the chair. And we need this type of compound when you have this type of patients. And the problem is the administration of this compound, we'll see. Because we need a control for a long time, not only for one day, but for example, for a week. And then we'll see some retard formulation in order to have a control for a whole week, We see. Other questions? Okay, we see next Monday. Okay, dear students, have you a nice weekend with the Alpini soldiers in Rimini, a lot of people. And then we'll see you next Monday.
Same to you, Prof. Bye-bye.
Okay, bye-bye, dear students.